Hello, this is the first of a few updates that I'm going to be going through today. Well, not today, but in the coming days, as I've been a bit caught up, reasons that I've listed in a post just below this one. And I sort of noticed that sometimes I tend to go into excruciating detail on every single line of code when I'm doing these kind of videos, so I'm sort of going to try and keep it short and sweet and more just be demoing what I'm actually doing. I'll obviously go through the stuff that needs explanation and some of the stuff that I haven't covered before, but I'm not going to go through every single line of code. The quality of this video is actually probably good enough that you could read every line of code you wanted to, and obviously in the final version I'll have commented all my code, but for now I'm not sort of going to go through everything. So if you think back to the last video I did, I sort of had some beat detection going, but I was using hard-coded numbers that only really worked with one sample. So that wasn't very good. That's not what I need. I need something that works generally across all kind of music I'm putting in, or all kind of, at least trying to get as good a reading from all kinds of music that you put in. So that's where FFTs come from, fast Fourier transforms. I'm not going to go over entirely what a fast Fourier transform is, because that is really complicated, and I don't even think I understand it fully myself. I'll probably link a website in the description to this, which is a DSP guide, which, you know, it talks all about the history of it and how it works and things like that. But in terms of the code, it's pretty much the same Maximilian code, except now I've got an FFT. The size of the FFT sort of means how many frequency bins are going to come out of it. So an FFT, it analyzes a sample and splits up into all the different frequencies that sample is outputting and puts them all into their little different bins, as they're called. So the size of the FFT determines the size of the frequency bins. The other two options here are the window size and the hop size. Both of them are sort of to make the FFT more smooth, to smooth out the results, and there's sort of a trade-off with how good the results you're going to get out of it and how computationally expensive it is. These were just default values that Mick had used in his example, so I thought, let's not mess with that. He knows what he's doing. I'll keep them the same. There's a few variables here that I'll probably go into discussion later when I'm actually showing what's happening. I'm going to leave the draw method for now, because obviously it's the audio requested method that I want to go through. So it's the same usual thing where I'm playing a sample back, but I've got this new thing here that's processing the sample, and the MFFT is my FFT. So what I'm doing in this is called spectral flux. What that basically does is it adds up all the frequency bins at one point in time and then compares them to the previous frequency bins. So basically, if there's an onset or a new note that's happening, then the number that I'm storing it in, which is called flux, which is just a variable, that should increase, and that will say, okay, so things are now, there's all the frequency bins added up greater than before, so that means there's been an onset of a note, or there's been at least some kind of movement. So it's pretty simple. What happens is you just go through all the frequency bins in the FFT with this for loop. You take it away from the previous ones, and then if it's greater than 0, so if there's been a positive change in the spectral flux, so if there's, you know, as I say, if it's detected a note or it's gotten louder, I don't think that's a scientific word to say it's gotten louder, but I guess in simpleton terms it will work for now. Then you add it to flux, which is just a variable, and here I'm just dividing it by the bins to get a sort of an average. And then this is some interesting code. This is what I'm drawing to the screen, so I'll go back up to the draw method in a minute. I've set a threshold, which is up here somewhere. Yeah, I've set a threshold, quite a low threshold, 0.1, and I'm setting the size of, I'm drawing a circle, ellipse up here, that's position, and I'm drawing it based on this size, array size. So I'm setting that to 100, when I'm saying the flux has become greater than the threshold that I've set, which is basically saying it's a note. And the thing here I've got, and weight equals 0. Weight is a number that I set to... Weight is 0 at the beginning, sorry. I don't set that to anything, but weight is a number. So when it detects a note, it will make the ellipse big, or give it a size of 100. I don't need this C out anymore. I was using that before I did the... before I actually started drawing something, and then it sets weight to 50. So that means that weight is now 50, and if weight is not equal to 0, then I start counting down again. So basically, weight is something, once it detects a beat, it sets a variable to a certain number, and then it starts counting down. And what that does is it means that if a beat is detected, depending on what you set weight to, will be how long it waits to try and detect another beat. So say if you have like a really loud sustained drum hit and the attack is quite long, if I set the weight to low, what is actually one drum hit will actually sort of count as 2 or maybe even 3 peaks in spectral flux. So what you want to do is set a variable so it's not picking up as many beats as are actually there. It's something you can mess around with. Even if you start setting it to an even higher level, it makes it so it picks up beats less often. I could even use it as a kind of a difficulty kind of measure for my game. And I also don't need to see that out anymore. And then here is just where I'm storing the current spectral, not spectral flux. I'm storing the current bins, all the bins added up together in an array called last FFT, and then that's what's used back up here for calculating, comparing the new one to the last one, and so on and so forth. And then I'm just outputting it. So yeah, I'll show you what that actually looks like. Yes, save all. Okay, so as you can see, when it detects a beat, it makes the size of the ellipse 100 by 100, so it makes it bigger. So this is with a weight of 50. So if I make that a smaller number, then it will be detecting beats more often. So if I set that to, say, 25, so you can see it's sort of detecting a beat when there isn't actually a beat going on. So it's sort of fine-tuning a number that's high enough so it's actually detecting beats that exist. If I set it to something like 35. Even then, it's still quite a high number because I've set the threshold so low. It's pretty much picking up anything as a beat. So it's both threshold and weight that sort of tell you how often it's going to actually trigger. So that's something that I'm sort of messing around with at the moment in a later version. I'm going to do some statistical analysis stuff later on to sort of work with the weight and the threshold to sort of get a good threshold, I guess, and get a good count on when beats happening, just to sort of make it blatantly obvious what this weight is actually doing. If I set it to a high number like 100, then it's not picking up a beat as often as it was. So that's it for now. I've got more videos on the way, but this is the first FFT type program I did. From there on, I've made a sort of a game based on it, but you will see that later. So see ya.